Thanks. Okay, hi everyone. I will be talking about HEP vectors and a simple HEP pipeline using vector. So right now we're here at in today's PyHEP. So you can run this talk on Binder from this, and you can visit the GitHub repository. So you can clone the Jupyter notebook locally and run it locally as well. I'll be talking about vector today. So a lot of information in this notebook is derived from the README of vector as well as the documentation of vector. So you can visit those and you can start it if you like the project. And we're also organizing a hacker shop related to at the end of PyHEP, I think on Thursday and Friday. And we have vector as a project there. So you can visit. Let me see where it was. You can visit the dashboard at Scikit-HEP. So if you go to the Scikit-HEP organization and navigate to the projects, you'll see a dashboard for the hacker shop where we've listed some beginner-friendly issues that you can pick up when the hacker shop starts. Okay, that brings us to our talk. So this talk is authored by Henry, Jim, and me, Saransh. I am an undergraduate at University of Delhi, and I'm not a physicist. So I like maths and CS, but I'm not a physicist by in academia or by profession. So I might not be able to handle the physics related doubt, but I'll be very happy to take up vector related doubts. Here are some quick links for the project, and I'll try to wrap it up in the next 20 minutes so that I don't take up the break time. Table of content. So introducing vector. This was also introduced by Jim in yesterday's talk, but he could not complete his talk due to time limitations. I would try to cover up those things as well, but I would not be covering uproot and awkward in that much detail. So vector allows a user to create 2D, 3D, and Lorentz vector, and it was initially created for HEP, but it is not limited only to HEP. So you can create 2D and 3D vectors or arrays of vector and perform any mathematical calculations on them, not just limited to HEP. The goals of this talk would be to introduce vector and its backend. So first introduce the vector and its backend, then introduce vector in a data pipeline, which would be using uproot, Scikit-HEP test data, and awkward, and see how all of that integrates. This is the setup that you can go through. You can we recommend running it on Binder, but you can also use Google Colab or run it locally. Okay, let's start by importing vector first. Vector comes with 3 backends: the object backend, the NumPy backend, and the awkward backend, and then Numba-based backends of object and awkward. So object type vectors can be created using the obj constructor or using the class method. So we have different classes for different dimensions of vectors. So vector object 2D, vector object 3D, and vector object 4D. I will be talking about them in a minute. You can use the class methods, which go like from underscore and the coordinate names ahead. So if you don't want to specifically include coordinate names in the constructor, for example, in vector.obj, we need to pass the coordinate names as well. You can use class methods for that. Using vector.obj and passing the coordinate names as well as coordinate values creates 2 vectors, like passing them twice, using the constructor twice creates 2 vectors here, both object types, and they inherit everything that a vector can do from the vector superclass. Similarly, you can create the vectors from class methods, and it works completely as it works with the obj constructor. And similarly, you can create momentum vectors by specifying momentum coordinates inside the constructor vector.obj. I think you cannot create momentum vectors from the class methods yet, but we are working on new constructors, so that might be possible in the future. And like, for example, if you vector knows when you want to create a momentum vector, if you specify only a single momentum coordinate. So for example, if I specify px and y, it will automatically create a momentum vector and not a normal generic vector. It created the momentum vector again. Going through the inheritance and superclasses of vectors. So it is best summarized using this graphical representation that is available in vectors repository. So every vector or every backend that you see is a subclass of the vector class and the subsequent dimensional class. So for example, vector 2D, vector 3D, and vector 4D. So the vector object 2D, and here you can replace object with any backend. So for example, NumPy or Awkward. And the vector object 2D will be inheriting from vector 2D, which would be then inheriting from the vector class. We can see that this in action here. So if we just print out the types of these vectors, we will get the object classes, which are, okay, let me clear these cells first. That would make much more sense. Okay. Go ahead. So we have the vector object XD classes for each type of vector, and the backend module was recently made public. So a user can extend these classes if they want to. So all vector classes are subclasses of vector. Every backend has its own vector backend XD class. So for example, vector NumPy 2D class and vector object 3D class, which is a subclass of vector backend. So vector object and vector NumPy. And all 2D vector classes are subclass of vector 2D and so on. So 3D classes in subclasses of vector 3D and so on. They should output true, as a vector 2D is a subclass of vector 2D, object, and object 2D. Similarly, we can do for planar, spatial, and temporal classes, which are available here. And momentum vectors work the same way as the normal vectors. The addition here would be that it would also be a subclass of momentum vector class and momentum object 2D vector class. Additionally, we can the coordinate classes are also subclasses of the top level azimuthal, longitudinal, and temporal classes, which can be seen from here. So there are no assert errors here. That means a vector 4D temporal will be a subclass of vector. The object would be, the class would be, the object that belongs to the class would be a subclass of temporal tau, temporal object, and temporal object tau. We will come to this back in a minute. Then we have vector methods and properties. So a vector introduces a lot of methods and properties. So a whole list of these methods and properties are available in the README file of vector. Let's quickly create a vector 3D object. And a good way that or a way that I prefer to look up these properties is by clicking tab after typing up the object name, and it shows up all the properties and the methods that can be applied. Another way is to go through the documentation, or you can click on this link and view the complete list. So let's say we want to gather the azimuthal coordinates. We'll start by obtaining the azimuthal object. So if here I click tab, there should be an azimuthal property here, and that can be used here to generate an azimuthal object, XY object. And let's say we want to take out the elements of this. We don't want it to be a class object. Rather, we want a tuple of elements. So the best way to go about this would be to read the documentation of that particular class. Here it specifies to use the elements property to retrieve the coordinates, and doing so would give us a tuple of the elements. So using this, you can use the vector package in any mathematical situation, not necessarily limited to HEP. And these are the allowed coordinate combinations, so a lot of them. And if you enter any wrong coordinates, it will automatically error out and tell you which are the correct coordinate types. We can similarly use the NumPy vectors. So the NumPy vectors would be a structured array. So vector provides vector.numpy_xt classes, so x for 2, 3, 4, and vector.array constructor can be used to create these NumPy classes. Additionally, vector NumPy_xt classes can be also used to create these vector objects. And currently, vector only accepts structured NumPy arrays. These arrays have a D type of object, so they are not that fast as normal NumPy arrays, but we can create arrays of vector using NumPy. So this would create a vector NumPy 2D object with this being x and this being y, this being x and this being y for all of these, and the D type can be specified like this. So exactly identical to how you create a structured array in NumPy. You can then pass the same thing to the class, and it would create the vector NumPy 2D object. And you can also use pandas like columns. So for example, passing in a dictionary and specifying X and Y values, and this should also create the NumPy vector as it was doing in the top two cells. Existing NumPy arrays can be viewed as arrays of vectors. So as these classes, vector NumPy classes, are these classes directly inherit the NumPy array. So the any operation that can be performed on NumPy array can also be ideally performed on these classes. And the existing NumPy arrays can be viewed as arrays of vector. But again, it needs to be a structured array. That is what vector can handle right now. So we can do this, creating a NumPy array and then viewing it as a vector NumPy 4D object. And similarly, we can use any, not any, but usually most of the NumPy methods should work on vector NumPy classes because they directly inherit the NumPy array. So reshaping it works as it would have done in the case of a NumPy array. We can then do a similar thing with momentum vectors, and it works as it is. So using the array constructor or using the momentum NumPy classes. Coming up to the awkward vector, similar to NumPy backend, vector also provides a vector array XD classes. So these classes inherit awkward array directly. So these classes are not mentioned in the this infographic here, but these are present in vector, and these are the ones that inherit awkward array directly. A vector provides two constructors to construct these classes, the objects of awkward vectors right now, which are vector.awk, or this can be vector.array. So vector.awk is just an alias for vector.array. And then we have vector.zip. So vector.zip acts as, so let me run this first. And this creates a vector array 3D with a jagged array with jagged data. So awkward allows us to create arrays of jagged data, which NumPy does not allow. So which is the data that HEP produces and which is that is required to analyze HEP data. Similarly, you can use vector.zip constructor, which is similar to ak.zip. Or another thing that you could have done was take vector.awk and pass in ak.zip with the contents inside. So this is what vector.zip does right now. Doing this would also create a vector array, which is a vector with jagged data inside of it. And similarly for the momentum vectors. And you can use the same properties that were being used on object and NumPy vectors. And additionally, you can also use awkward arrays, methods, and properties because this directly inherits an awkward array. Going to vector.azimuthal, it would return an azimuthal awkward XY array. And then similarly, if you want elements, you could do elements, and it should return an array of elements. Vector.x would return the x value, and x would again be an array because our initial object was a vector of array, an array of vectors. Let's say if you don't want to use the vector constructors, you can do it. You can do the same thing with awkward.array, but in this case, you will need to register awkward. So here, vector would add all the vector behaviors to ak.behavior, and that would allow awkward to construct vectors just by passing a name here. So you could do with name 3D, with name 4D, and pass in the same parameters. This would work as well. And the same way as momentum vectors. Moving on to compiling vectors with Numba. So vector also comes loaded with Numba-X backend. So right now, vector object and vector arrays are compatible with Numba, and vector NumPy is not compatible with Numba. At the time of writing vector, there was an issue that was blocking vector NumPy running on Numba, but now that issue is solved, and we hope to see a NumPy backend in the future. So what Numba does is it pre-compiles or just-in-time compiles your Python code. So Numba ships LLVM, and it compiles your Python code. So it makes it faster. First, when you run the code first time, it compiles it and executes it. When you run the code second time, it executes from the compiled code, making it much faster. But here in case of vectors, it would require you to actually have millions of vectors to see the effect of speed up. Otherwise, it might also end up being a disadvantage. Passing in the vectors in a function which is decorated by the decorator ngid, which is provided by NumPy, it would make it possible to just in time compile that operation. And Numba only works with specific or a subset of NumPy and a subset of Python, so it is not it cannot be used globally, but it can be used on a subset of NumPy and Python. That works as well. Computing mass. So we are passing into vector objects and we are adding those vector objects and computing the mass. Now this would work. This would ideally work even faster the second time because Numba has already compiled this up. We can do the same with awkward, as we have an awkward Numba backend right now. Let's say we create an awkward vector using list comprehension. So we'll have a length of 50 and the inside data would be randomly chosen. The length of the inside data would be randomly chosen. So it would be 0 also, 0, 1, 2, 3, 4. I think, yes. So the first element is an empty list and the length would always be 50 as we're specifying it here. We can then use vector.awk to generate a vector array object. So if I print this out, this would be a vector with a momentum vector with jagged data, and we can print out the fields and type of it. So here the type means we have variable length lists of momentum 4D vectors. I'll be touching it up ahead, and the fields just mean that we have 4 fields x, y, z, and t as specified here. Momentum fields that are labeled as x, y, z, and t inside of vector and awkward. We can do the similar thing here. Use Numba and pre-compile just in time compile this, and if we run it the second time, this should go much faster. And again, you would require like a lot of vectors or a list of like 1 million vectors to actually see the difference in speed while executing a normal Python code and while executing a Numba code. Moving on to a pipeline that uses uproot, awkward, and vector. So a brief introduction. Uproot is a pure IO library that can read and write root files. Awkward is the library that handles jagged data, which is like the NumPy for jagged data, and vector is the library that can create Lorentz vector, which are required in the analysis pipeline of high energy physics. We'll start by importing escape test data, which would allow us to download data from the GitHub repository of scikit-hep test data. So it comes loaded with a lot of different root files which can be used inside your workflows. And we'll start by importing uproot. So looking at the keys of the retrieved data. So we have loaded the uproot hgz.root file, and we can look up the keys. We only have a single key events, and that events key corresponds to a T tree that has a lot of branches with a lot of data inside it. Now we can, this is a T tree with 51 branches. We can look at the branches here. So we can extract the actual data in the form of awkward arrays, and I've already introduced awkward arrays, and awkward arrays are fast. So they're not like normal Python lists. They are like the NumPy of jagged data. We can use trees.arrays, and again, like Jim mentioned in his talk yesterday, we can pass in what we want. So for example, if you want only fields corresponding to muons, we can do something like this, and it would only load up the fields that have muons. The fields dealing or the branches having the muon data. Let's load up all the branches right now, and let's look at the fields that we have. So we have a lot of fields. So if I had specified muon underscore star, it would have loaded only these fields, and I don't know about edmuon, but I think it would have loaded only these fields. Let's look at specific fields. For example, muon underscore px. Every field corresponds to an awkward array itself. So muon underscore px is an awkward array, and we can construct a vector using vector.zip and passing in all these awkward arrays as the argument or a dictionary values in the dictionary. So now we have a momentum array 4D. Let me print that up. We have a momentum array 4D object, and you can again go through the types, fields, and if you go through the type, so here 2421 star var means that we have 2421 lists of momentum 4D with each list having a variable. And then again, going through the same operations that we went through object vectors and NumPy vectors, we can also transform vectors to other coordinate systems. So for example, to rho phi theta tau, and looking at the fields, we'll have rho phi theta and tau. We can also in the dimensions by using 2 vector 3D, 2 vector 4D classes. So these all methods are listed in the readme vector. And then we can slice these. So these are awkward arrays and a list of mu1 vectors. We can slice these as we want. The length of both of these are different. That means we do have a variable length list. And we could have also checked that from the type of this indexed object. As the first list had only one element, hence an index of greater than 0 should show an error. So here we would get an error because we're trying to access index out that does not exist or is out of bound. Let us create a mask which will select all events with 2 muons. So ak.nums provide would allow us to create a mask that would filter out events which only have muons. We could have also done something like muons dot n muons, if I'm not wrong. If this was the field equal to 2, this would have also worked as well. And again, to go through the documentation, you can use the documentation to go through examples and how the method works. If you apply that mask to our original muons, we'll get all the events which have exactly 2 muons, and then we can filter out these events, these 2 muons events. So this would be the first muon, and this would be the second muon, using slicing the list in a 2D fashion. And then we can use methods from vectors such as delta r to compute actual physics. Let's say we do mu1 delta r mu1 2. So compute all the delta r values. So if I print that out, it would again be an awkward array, and then we can plot this up. That shows up nicely. We can adjust the bins as we want. Yep, so this was a small example of how you can use vector with uproot and awkward in a data analysis pipeline. So we started by taking out the data using uproot, and then manipulating that data with awkward, and then converting that data into Lorentz vectors, using the muons and the events using a mask to segregate events with exactly 2 muons, going through these events and going through these muons and taking up the first muon and second muon, and then performing a delta r operation between them to generate another awkward array, and then we at the end plot it. So moving ahead, there have been some recent developments in vector. So vector v0.9 is out, and v0.10 is out. So if you're using vector, you should upgrade to this version. v0.10 removes support for Python 3.6, and you can read more about these developments in the changelog of vector. There also are some future development plans for vector. So we are working on better constructors. Benchmarking suite is a possible future development plan. Then benchmarking against root. We will also be providing a complete Awkward v2 support as soon as Awkward v2 is released, which is scheduled for December. Then a NumPy Numba backend that I talked about, and other potential backends. So, and it was Vector's first major release was scheduled before PyHEP, but we couldn't. That was unfortunately delayed. A major release can be expected in October, which would be introducing the new constructors primarily. And again, you can reach out if you're stuck anywhere using GitHub discussions or Scikit-App Vector GitHub channel or the issue tab of Vector. I think that would be it from my side. I think it was a bit fast-paced, but I hope you got the gist of it.
Yeah, thanks a lot for this really nice notebook, and seems like it has been lots of progress and it's really a great library useful for many applications. There's one question from Eduardo and Slido. So he reiterates a work suggestion to make a phase-space work and profit nicely from vector.
We can definitely add that.
That's planned.
We can add that to future development.
In fact, I can talk. Yeah, it's nicely because when you generate simulation toy samples, if you can then manipulate them properly for vectors rather than just quote unquote random lists, it will be so much nicer, right? So that's actually something. That's what I mean. It closes the loop in something that is needed in workflow of what we have to do quite often. So if it's already on the to-do list, that's fantastic. Thanks.
Probably it's in the TensorFlow backend, right? That would make this happen.
Is that a phase-space addition or a vector addition? It's unclear from your question.
I think it's just a bridge in the same way that we have the bridge now between decay language and phase space. I believe it's probably just a functional tool to be able to output. I think it's more of a phase space development in the end. So